Okay, let's take a look at the remainder theorem. Remainder theorem says essentially that if you take a function f, let it be a polynomial, and if it is divided by a linear factor, x minus c, then if you evaluate the function at the c value, so really if you take x minus c, set it equal to 0, get x equals c. So if you do f of this number here, the remainder will be that function value. So the same thing as dividing x minus c into the function, whatever remainder you get is the same thing as just taking solving this simple equation and evaluating the function at that number. That'll give you the remainder. Let's look at a simple example. We've already seen this function a couple of minutes ago on a different video, where we had that this is our dividend and this is our divisor, and we said that x plus 3 times x minus 9, these are the factors that multiply together to give you this. Well, it's known that if I take this factor here and set it equal to 0, if I take f of negative 3 and plug it into this function, I should get 0 because we said that this is a factor. So the remainder would be 0. So we could do the long division, which we did in an earlier video, and we got a remainder of 0 when we divided x plus 3 into this polynomial. A shortcut way is to take the divisor, set it equal to 0, and evaluate the dividend at that value. That'll determine the remainder. So let's just do f of negative 3, and if I plug negative 3 in, I get 9 plus 18 minus 27, which is equal to 0. Let's look at the second one. Here we have a cubic. We have a divisor, which is a polynomial. So again, if I set x minus 2 equal to 0, I get x equals 2. So I want to evaluate my function at 2. So in the graphing calculator, I've already plugged the function in. I'm going to go to table set, and I don't care what the table start is or what the changing table is. I'm going to use the ask function, which in this case, I'm going to ask it to evaluate the function f at 2. So the table has been set, so now I go to table, and I plug in 2. The remainder is 23. So that means when I evaluate the function at 2, I get 23. And the remainder theorem says that if I was to divide x minus 2 into this polynomial, I would get a remainder of 23. We looked at this quotient at an earlier video. Let's take a look at what that remainder would be. Let me just set that up. So here's our function, and then we're evaluating it, we're dividing 2x minus 1 into it. So the question is, what is the remainder when 2x minus 1 is divided into this polynomial here? Well, if I solve this simple equation, hopefully you'll see that I get 0.5. So let's plug in 0.5. So I plug the function in. Again, I don't really need to reset this, but if you change something, I don't care what the starting value is or the changing value is. I'm going to use the ask menu on the independent variable, independent being the x value. Dependent is always on auto. I've never had it on ask. I don't actually know what that does. And I go to graph, and I'm going to get rid of the value that's already there, or I'm going to delete it. Excuse me. Should delete. No, it doesn't delete. Doesn't matter. I plug in 0.5, and the number I want is negative 1. Why doesn't that delete? There it goes. It deleted it. So 0.5, I didn't mean to do that, is negative 1. So that means f of 0.5 is equal to negative 1, or when 2x minus 1 is divided into this polynomial, my remainder is negative 1. And if you look back at the previous video, you'll notice that that's the case. Factor theorem is just a special case of the remainder theorem. All it says is that if you evaluate the function at the root value of the divisor, meaning again taking x minus c, setting equal to 0, I get x equals c. So if I take that value c and I evaluate the function at that value, at that number c, and if I get 0, then that means x minus c is a factor of the function. Also says that when I take x minus c and divide it into the function, I get a remainder of 0. So the remainder theorem just gives you what the remainder is. The factor theorem is a special case of the remainder theorem. It just says that if your remainder is 0, or if you evaluate the function at a number and that value is 0, then that means this c is a factor of the function. So here's my function right here, 2x cubed minus x squared. You can read it. And we just want to know, is x minus 1 a factor of this polynomial, and is x minus 2 a factor of this polynomial? So let's plug it into the graphing calculator. So I plug the function in. I'm going to go back to table. I'm going to get rid of this value here and this one here. It says, is x minus 1 a factor? Well, that means we plug in 1, not negative 1, and we got 0. So that means f of 1 equals 0, and therefore we can conclude that x minus 1 is a factor of f of x. We also can say that x equals 1 is an x-intercept. And that's pretty easy to tell. If your function value is 0, then that means 1 has to be an x-intercept. So not only is x minus 1 a factor, but the root value of the divisor 1 is an x-intercept. You could also say, as opposed to x-intercept, you could say it is a root or it is a 0 of f of x. The next question, is x minus 2 a factor of this polynomial? So let's just evaluate the function at 2. We get 13, so therefore f of 2 equals 13. That means x equals 2 is not a 0 of f of x, or x minus 2 is not a factor. So really in this case all we used was the remainder theorem. We weren't able to use the factor theorem because we didn't get 0, we got 13. So the only difference between this problem and this one is this one actually uses the remainder theorem and does the factor theorem at the same time, and since we have the remainder is 0, then that means x minus 1 is a factor. Here we weren't able to use the factor theorem because we got a non-zero remainder, we got 13, so therefore we don't know that we know that x minus 2 is not a factor of that polynomial right there. So here are some statements regarding a function and a real value c. C is a solution to f of x minus f of x is equal to 0. So if I take the function and set it equal to 0, that means c is going to be a value that gives you that. C is a 0 of f of x. C is a root of f of x. So these two, 0 and root, those two words are interchangeable. So therefore, if c is a 0, then that means x minus c is a factor of f of x. When x minus c is divided into f of x, your remainder is 0. That's the factor theorem right there. C is an x-intercept on the graph of y equals f of x. Okay. So just a little side note here, a theorem. A polynomial function is of degree n. So that means we have some polynomial function, f of x equals x to the n plus some number a sub 1 x to the n minus 1 plus blah 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 plus a sub if that's a sub 1, we'll make this a sub w, and this is x plus a sub z. Doesn't really matter. Where a's are just numbers and x's are obviously your variables and n's are your exponents. So this is to the first power, and that's 0, x to the 0. If this is my polynomial function, it has at most, the most number of x-intercepts or real zeros you can have is n, which would be the degree of the polynomial. If you think of a quadratic, the most number of, at most, quadratic could have at most 2 x-intercepts. Obviously, it could only have 1 x-intercept, or it could have no x-intercepts. So that's all this theorem is saying right here. So here's the general form of a polynomial that I was trying to write in the previous example. Rational zeros theorem, I like to put the word in front of this, possible rational zeros theorem. This says that we have a polynomial of degree 1 or higher, meaning we're not talking about a constant function, y equals 3. We're looking at least a linear function, which would be 3x plus 4, and onwards, the quadratic, cubic, onwards and upwards. If this is our polynomial, where the a sub n, which is this term, the coefficient of x to the n, is not equal to 0, and likewise the constant term down here is also not equal to 0. And each coefficient is an integer, so all of these values are integers. if P over Q is in lowest terms, where P is a factor of a sub 0 and Q is a factor of a sub n, if P over Q is in lowest term and it is a rational 0 of f, so that means when I evaluate f at P over Q, I get 0, so therefore I'm using the factor theorem. P must be a factor of a sub 0, that's what I already said, and Q must be a factor of a sub n. So if a function has rational zeros, you know that it must be of the form, it must come from the factors of the constant term and the factors of the lead coefficient, whereas the factors of the constant term divided by a factor of the lead coefficient. And you put it in lowest terms just because nobody puts, writes fractions in non-lowest terms. Okay, so let's look at an example. Let's first list the actual rational zeros using this theorem, which just says find the factors of the last one, find the factors of the lead term, and then just divide them, P divided by Q. And therefore, those are your list of possible rational zeros. What do I mean by rationals? Nice numbers. Rationals are going to be of the form 3 halves. You could have decimal equivalents, 1.5 and 0.3 repeating. Those are all considered rationals. Irrationals, which is an opposite of rational numbers, would be numbers like pi, the square root of 3, the very famous number e. These are all considered irrational because the decimal approximations, they're just decimal approximations because they do not repeat and there's no pattern. Just like pi does not repeat or has no pattern to it, its decimal part. So all my answers, if we have nice answers, which are considered rational numbers, which could be integers or could be fractions or could be decimals, where the decimal part either terminates or repeats, your rational roots are going to come from the factors of the constant term and the lead coefficient. So let's use the rational zeros theorem, where my p-values and q-values, they come from the factors of the constant term and the lead coefficient. So what are the factors of the constant term? Well, in this case, my constant term is 5. So the factors are 1 and 5. Well, it could be positive 1 and negative 5, or it could be negative 1 and positive 5. So we just write down plus or minus 1, plus or minus 5, and we'll deal with that later. So so now my q values come from the coefficients of the highest degree term, which in this case is 3. So therefore it's 1 and 3. Well, clearly it's positive 3, so it could be plus 3 and plus 1 and plus 3, or negative 1 and negative 3. So we always just write down the positive and negative of each factor of each term. And now we want to find p divided by q, so we want to take every p value and divide it by every q value. So we do positive 1, plus or minus 1 divided by plus or minus 1, we get plus or minus 1. Plus or minus 1 divided by plus or minus 3 is plus or minus a third. And plus or minus 5 and plus or minus 1 is plus or minus 5, and plus or minus 5/3. So this is a list of my rational zeros. And again, I like to write the word possible rational zeros. So these are possible rational roots. You don't necessarily have to have rational roots, meaning you don't necessarily have to have nice answers. Sometimes when you have a quadratic, you don't have nice answers because you get radicals. But where do you get radical solutions when you're dealing with quadratics? The quadratic formula. So you're not necessarily always going to have rational or nice roots. Sometimes you may have irrational roots, which in this case will come from the quadratic formula for dealing with quadratics. But here is the list of possible, they're not actual roots, they might be roots. Clearly this is a quadratic, so it's only going to have 2 roots. Here we have 8 possible roots. We only, at maximum, we could only have 2. So again, this is just a list of possible rational roots. So again, let's find the list of possible rational roots. So possible rational roots. My p-value is the factors of 9, which is plus or minus 1, plus or minus 3, and plus or minus 9. My q-value is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And it's customary to write them in increasing order from left to right, starting with 1. So now I take this 1 and I divide it by every q value. So I'll put a little division symbol here. So 1 divided by 1 is plus or minus 1. 1 divided by 2 is plus or minus half, plus or minus a third, plus or minus a sixth. Then we do 3 divided by 1. I'll use a different color. So we do 3 divided by 1 is plus or minus 3, plus or minus 3 halves, plus or minus 3 over 3, plus or minus 3 over 6. And then we'll use green. We do 9 divided by 1, plus or minus 9 over 1, plus or minus 9 over 2, plus or minus 9 over 3, plus or minus 9 over 6. So let's simplify some of these. So this is plus or minus 1, plus or minus a half, a third, 3 halves. 3 over 1 is the same thing as just 1. We already have 1. 3 over 6 is the same thing as 1 over 2. We already have 1 over 2. 9 over 1 is just 9. 9 halves is unique. 9 over 3 is equal to plus or minus 3, which we already have. And 9 over 6 is 3 over 2, which we already have. So you don't need to write it down twice. So it's customary to rewrite your list with all the unique possible rational roots. Since, where is my pen? There it is. It's not black. Okay, so plus or minus 1, plus or minus half, plus or minus a third, plus or minus 1/6, plus or minus 3, plus or minus 3 halves, plus or minus 1 we already have a half, we don't have plus or minus 9, plus or minus 9 halves, we already have plus or minus 3, we already have plus or minus 3 halves. So this is the list of the possible rational roots of this polynomial right here. Obviously, there are 2, 4, 6, 8, 10, 12, 14, 16. There are 16 possible rational roots. This is a cubic. The most number of roots of any kind are only 3. But we could have some rational roots, and if we have any nice rational roots, they're going to come from this list of, I guess, 18 I said. But we don't know if we're going to have rational roots at all. You might have rational roots, you might not, but if you do have a rational root, it'll come from this list right here. Determine the list of the rational roots and show that it has no rational roots using the rational root theorem. So let me erase that and then we'll go on. So first thing I want to do is find the list of the possible rational roots. So possible rational roots. And let me move the screen down here. So using the rational root theorem, which gives our possible rational roots, the coefficients of my p-values was the factors of 2, plus or minus 1 and plus or minus 2. My q-values are the plus or minus the factors of the lead coefficient, which is just plus or minus 1. So we divide those two, we get plus or minus 1 and plus or minus 2. I now want to use the remainder theorem and the factor theorem, where the factor theorem is just a special case of the remainder theorem. If you get a remainder and the remainder happens to be 0, then that means you know that you have a factor or an x-intercept of the polynomial. Here we want to show that there are no rational zeros. So we want to take our function f and evaluate it at 1, at -1, at 2, and -2. Okay, so here's my function that I've typed into the graphing calculator. Again, go into table set. I'm going to ask specific values, 1, -1, 2, and -2 from right here. So it doesn't matter what these two values are. I just want to make independence on ask and dependence on auto. I then want to go to the table. I'm going to get rid of what I already have there. And so I'm going to do +1, -1, +2, and -2. So I get 2, 2, 8, and -4. 2, 2, 8, -4. Let's make sure that's right. 2, 2, 8, -4. Perfect. And we have no rational zeros using the rational zero theorem. So therefore we have no roots. And we just want to, so really we were just exercising using the rational root theorem, the remainder theorem, and the factor theorem. Okay.